Get close for this because it's going to be spectacular. Thanks for joining us for this year's Shoemaker lecture of the Planetary Sciences section of AGU. This lecture honors the memory of Gene Shoemaker, really the father of astrogeology. Gene's legacy of scientific excellence and his drive for discovery are very much in line with AGU's core values. For this year's Shoemaker lecture, we're very pleased to have Sean Solomon as our speaker. Sean is Director Emeritus of the Department of Terrestrial Magnetism of the Carnegie Institution of Washington, recently stepping down after 9 years of service as director. Prior to that, he was a professor at MIT for more than 20 years. Sean is a seismologist, a marine geophysicist, and a planetary scientist. He's worked on a wide range of problems in earthquake seismology, geodynamics, magnetism, and the geological and geophysical evolution of the terrestrial planets. He has served on the science teams for NASA's Magellan mission to Venus and the Mars Global Surveyor mission. He's currently a co-investigator on GRAIL and the PI of the Carnegie Institution team of the NASA Astrobiology Institute and for NASA's Messenger mission, which we'll get to hear about today. This mission, as you know, is the first mission ever to orbit the planet Mercury. Sean is a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, and past president of AGU, not just the Planetary Sciences section, but the whole darn thing. So amazing. Many, many honors and awards, the Arthur Day Prize from the Academies, the G.K. Gilbert Award from the Geological Society of America, the Harry Hess Medal from AGU, among many other honors. I hope you're all looking forward to hearing this as much as I am to see the hot off the presses scientific data from Messenger. Let's welcome Sean for his lecture entitled Messenger, Exploring the Innermost Planet. Sean.
Thank you very much, Lori. It gives me great pleasure to take this annual occasion to remember Gene Shoemaker, who taught us much of what we know about impact craters, about the geological history of the moon, and by inference all of the inner planets, about the population of comets and asteroids in our solar system and the entire history of impact cratering. Every day that we study the planet Mercury, we make use of the ideas and the work that Gene laid down, and we miss him. I want to take my hat off to Jeff Marcy for bringing us up to date, even more up to date than this slide, of the wonders of extrasolar planets, and to point out that on some plots, this is orbital eccentricity versus semi-major axis, Mercury falls squarely in this growing cloud of wonderful new data on extrasolar planets. Jeff's smallest planet, of course, is still 2 orders of magnitude larger than Mercury. But Mercury is our solar system's laboratory for studying processes that are involved in planet formation and planetary evolution near the host star. So it's a wonderful place to test ideas for planets forming near their host star and to look for ways that aspects of Mercury's behavior might guide observations of near-in super-Earth and Earth-like exoplanets. I think just by way of introduction, all of us know that Mercury is a member of the inner planet family, that it's about 5% of an Earth mass, and is the only other inner planet to have a global magnetic field. Many of these facts have been known for some time. You see a quote over there that's hard for me to read from this angle from Harold Urey 60 years ago. And we haven't advanced very much beyond what Harold was able to say about why the densities of the inner planets differ the way they do, but it's been known for all that time that Mercury's high density required that it formed somehow with a very large fraction of iron, and by inference had a very large fraction of its interior made up of core. Now, I want to run you through a wonderful range of conclusions and findings, some of which haven't quite yet been interpreted to the point of conclusions, that we're learning from orbital observations around Mercury. As Lori said, Messenger is the first spacecraft ever to orbit the innermost planet. It went into orbit last March. Some of our early findings were published 10 weeks ago in a series of papers of Science magazine, and I'm going to include some of those for completeness, but much of what you will hear today is new and hasn't been presented before. But I want to say that I can only give you a snapshot of all that is being presented about Mercury at this meeting. There are 63 papers being given at this meeting by the Messenger team, many of them in a poster session going on right this minute. And a number that will be given, 20 in fact, in 2 oral sessions over in Moscone West this afternoon. So for a lot of the details, please visit the posters after this talk or during if you wish, and come hear the Messenger session this afternoon. Okay. Listed here on the left is an outline of what I hope to accomplish. It will be a challenge to do so. But I want to touch on each of these topics in turn and show you how many of them are related and that our view of all aspects listed here of the innermost planet has been changed by the observations we've been able to make from orbit. But let me start with Mercury's surface composition and the surprising results that we're seeing a much higher fraction of volatile materials than we expected on the planet closest to the sun. There are 2 primary tools that are used for this geochemical remote sensing. One makes use of solar X-rays to excite the atoms of the surface to fluoresce at X-ray wavelengths, the X-ray fluorescence method. And that produces spectra like these, and from the paper by Larry Nittler and others, where the peaks are associated with fluorescent X-rays from the surface convolved with the instrument response. One makes a forward calculation using the instrument response and other aspects of the spacecraft to compare with the spectra measured from the surface. One measures the solar incident X-ray flux with a separate sensor, and you see that there are peaks for many of the major rock-forming elements. This also is from Nittler et al. It is a plot of a number of large areas on Mercury as measured by the elemental abundances of magnesium and aluminum. Here, a reference to silicon because the ratios are determined better than the absolute values. And they're compared on this plot with a number of other samples and averages for the Moon and the Earth. And on this plot, the various areas, by the way, these are all measurements taken during solar flares, which are particularly energetic and therefore excite some of the hard X-rays that are needed to see some of the high Z elements like iron and titanium. A first-order comparison is that the Mercury results do not look like the Moon, in particular like the lunar highlands, and the aluminum-silicon ratio is much, much less than the Moon. Mercury's crust is not dominated by feldspar. The other thing you can see is that these plots on this diagram fall midway between typical basalts, lunar or terrestrial, and more mafic to ultramafic rocks, notably the komatiites, which many of you know are rocks, igneous rocks that formed early in Earth's history by high degrees of partial melting of the mantle and the eruption of high-temperature magnesium-rich lavas. But remember that these are spatial averages. I'll show you that here. Also from Nittler et al. Here you see the footprints of the X-ray spectrometer that produced the observations depicted on the previous slide. Messenger's in a very eccentric orbit around the spacecraft, high above the planet in the southern latitudes and close to the planet only at high northern latitudes. So the footprints can be quite large if the flare occurred while the instrument was looking at the planet from high in its orbit. And the footprints can be small if the flare occurred coincidentally when the planet was in view at a lower point in Messenger's orbit. But you see also that there are spatial variations in the magnesium-silicon ratio, portrayed here by color, indicating that even at these large scales, you can see that there are compositional differences that in potential can be mapped. I'll come back to that later. Here's a similar plot, only now we've just plotted calcium over silicon versus aluminum over silicon. And again, the Mercury spectra do not match those of the Moon and are midway between basaltic materials and more mafic materials. this is an illustration that there is quite a bit of sensitivity to the elements titanium and sulfur, as well as iron. Although titanium and sulfur don't have resolvable peaks in these X-ray spectra convolved with the instrument response, they're on the shoulders of other peaks. And changing the forward model, in the case of titanium by a few tenths of a percent, in the case of iron or sulfur by a percent or so, can be distinguished on the basis of goodness of fit. And so this gives you a sense of how well individual spectra yield individual results, and is illustrative of the two general surprises that we got out of the X-ray spectra. Iron and titanium are lower than many previous predictions, and sulfur is substantially higher, 1 to 4% sulfur on the surface. That's more than 10 times the average terrestrial value. Interesting, the sulfur correlates on a spectra-by-spectra comparison with calcium and less so with magnesium, suggesting that perhaps the sulfur resides in sulfides of calcium and perhaps magnesium on the basis of these correlations. I'll come back to this point. The second instrument of interest to us is the gamma-ray spectrometer, which measures gamma rays from natural radioactivity, which I'll talk about here, as well as gamma rays from the interaction of cosmic rays with surface materials. Here you see a comparison of two spectra taken from a paper by Peplowski et al. The same spectra taken just at two different elevations above the planet. Many of the peaks you see have to do with spacecraft components, but I draw your attention here to the potassium and silicon peaks, which are enhanced when the spacecraft is closer to the planet, and therefore you're seeing a planetary signal. You can remove the spacecraft effects by using the high altitude data. And what is found is that the potassium-thorium ratio on Mercury is in the same family as that for Mars and Earth. Potassium, unlike some expectations, is not depleted relative to thorium and uranium as it is on the Earth's moon. So this is another vote in favor of retention of moderately volatile species like sulfur and like potassium, and contrary to the expectations of many of the ideas for how Mercury formed. Depicted only in cartoon form here, you see the repeat of these measurements. Much of the thinking about Mercury before Messenger went into orbit involved high temperature processes, a hot solar nebula, high temperatures imparted by the condensation process, high temperatures imparted during giant impact. Now, the jury's still out on giant impacts because experts have taken us to task for jumping too quickly on ruling those ideas out, because giant impacts tend to be short-term events that may permit the preservation of volatiles, and we look forward to those kinds of models. But a suite of models from the literature can now be ruled out on the basis of their prediction of volatile depletion, contrary to what Messenger sees. The fact that we see sulfur in with the silicates has been taken to suggest that the precursors to Mercury are very likely the products of highly reducing conditions under which sulfur does, to a substantial degree, reside in the silicate rather than the metal phase under equilibrium separation conditions. Okay, let me jump next to internal structure. This has not been published. But these are some new results being presented later today in other sessions. First, topography. We're building up wonderful maps of the topography of Mercury's northern hemisphere with our laser altimeter. There's a northern lowlands clearly seen around the North Polar region. But there's more than something like 10 kilometers of relief, a unimodal hypsometric curve. So there are uplands at lower latitudes and a variety of interesting terrains, many produced by the impact cratering process, but many not. Here's a current depiction of Mercury's gravity field. Remember, Messenger's in a highly eccentric orbit, so the gravity field is much more robust in the northern hemisphere and has been damped in the inversion solution in the southern hemisphere. But you see large excursions in the gravity field, some very pronounced positive gravity anomalies in the northern hemisphere, many of them, several of them, coinciding with impact basins, so these are Moscone-like anomalies on Mercury. Greg Newman, in a parallel session, is presenting this map, one of a suite of possible maps of crustal thickness on Mercury that satisfy the gravity and the topography, subject to some assumptions. The assumptions are given at the bottom for a modest density contrast, positivity constraint that the crust never go negative. You get these kinds of solutions for the gravity, for the crustal thickness on Mercury. The general result is that the crust is thicker at low latitudes and thins toward the poles beneath the northern lowlands. There's also some evidence for crustal thinning underneath some of these large Moscone-like basins. Now I want to talk about the deeper structure. The gravity field yields solutions for two key parameters, together with other observations, notably the radar observations of Mercury's spin state by Jean-Luc Margot and his colleagues 4 years ago, and subsequently, that helped determine the obliquity and the amplitude of the forced libration of Mercury. This moment of inertia is larger than many predictions of interior models. This is close to the number that Margot wrote about in 2007. But this combination of these two parameters is not met by any model for the interior structure of Mercury in the literature. And I'll show you the difficulty with some work of Steve Hauk being presented this morning. Hauk produces a number of forward models of Mercury's interior structure that use equations of state and starting assumptions for densities at the top of individual layers. So if you take a standard model for a planet like Mercury, in which you've got a silicate shell consisting of the crust plus mantle overlying a core consisting of iron plus some lighter element, or more than one lighter element, you can make predictions for the moment of inertia shown here, and for the ratio of the moment of inertia of the solid shell of the planet that participates in the 88-day forced libration over the polar moment of inertia of the full planet. This comes out of Stan Peel's theory and Jean-Luc Margot's measurements. You can test many models, here something like 1 million, against the observations with their error bars. And you can marginally fit these observations, the C over mr squared that comes from the gravity field, and Cm over c that comes from the spin state and the gravity field. And, but most models do not fit. Moreover, the average density of the silicate shell is high. You can see that from the colors, 3,500 grams per kilograms per meter cubed. That is a problem. The problem is that we don't know how to make silicates dense except with the abundances of iron and titanium and aluminum in phases such as garnet. And the X-ray results are telling us that the lavas at the surface of Mercury are low in iron, low in titanium, and comparatively low in aluminum. And so if they are products of melting of this mantle, then that mantle can't have these elements in it, and it's difficult to come up with this kind of high density. That has led the team, and again I refer you to Hauk's poster, to a different kind of model, a model in which the outer shell consists of silicate plus some dense layer at the bottom of the stack, and that overlies an outer core that is fluid and an inner core that may be solid, and satisfies the usual boundary conditions and equations of state. What could that solid shell be? Well, here's one idea, but we're open to others. And that is that it could be FES. Now, how could that be? Under the reducing conditions that we think held in order to impart the high sulfur abundances to the surface, sulfur and silicon can partition into the metal phase during metal silicate segregation. Moreover, at low pressures, pressures less than 15 GPa, under melting conditions, you can get two immiscible liquids, one sulfur-rich and one silicon-rich. Here's a diagram from the literature, and you see these loci of the tie points of coexisting liquids at each pressure in the FES-SI system. If sulfur and silicon are both in the core, one can get some interesting layering results, and there are some conditions on composition and temperature that would permit the top layer not only to be FES, which is less dense, but to be solid today. Now, that may or may not be the answer, but it's an answer that does fit, as shown by Hoax Calculations. Here's a recalculation of the fit of the models to the observations. You still get a high density for the average solid shell, but now that average solid shell includes a crust, a mantle, and a dense layer, possibly FES. And so the kinds of models we are thinking of look like this, with a crust that we can see and remotely sense, a silicate mantle, a solid FES layer, and then an outer fluid core and possibly solid inner core. This solid FES layer would have some interesting implications for the attenuation of the magnetic field generated by a dynamo in the fluid layer, as Christensen has written about. It might have some implications for the geometry of that field. I'll come to that. But in any case, the depth to the decoupling layer for the 88-day libration, the thickness of the solid layer, including the dense layer, is only 400 kilometers. So all of the silicate action has to take place in an outer shell that's less than 400 kilometers thick, and most of the planet, as much as 80%, if we count this layer, is core. Go to Steve Haug's paper. Okay. Internal magnetic field. I'll go quickly through this because this comes from a published paper by Brian Anderson. Of course, we've known that Mercury had a magnetic field since Mariner 10. As you can see, messengers in this quite eccentric orbit that goes in and out of the magnetosphere on each orbit and comes as close as 200 kilometers to the planet. And when the spacecraft is close to the planet, you see the planetary field, and it's beautiful and it's dipolar. But to distinguish among ideas for how the magnetic field is generated, we want to know the higher order coefficients, the shorter wavelength components. And that has been a challenge. It's been a challenge from flyby data alone because the dipole term and the next term in the expansion, the quadrupole term, do not separate cleanly in inversions. And it's been a problem even in our data sets because of external magnetic fields driven by magnetospheric current systems and because of our eccentric orbit. And so the magnetometer team, led by Brian, has had to take an alternative approach to estimating the next term in the expansion. And they did that by making measurements of the magnetic equator of Mercury. Under these assumptions having to do with the symmetry about the magnetic equator of magnetospheric current systems and time averaging of the effects of variable interplanetary magnetic field, they made measurements over an entire Mercury year of the position of the magnetic equator, determined by the place where the magnetic field is parallel to the spin vector of the planet. And as you see, there's a very consistent result that the magnetic equator is offset from the geographic equator by almost 500 kilometers to the north. And so the magnetic field can be fit by an offset dipole or equivalently by a dipole and an axial quadrupole. But the main result is that the magnetic field, although almost perfectly axisymmetric, is strongly asymmetric about the equator. The field in the north polar region is more than a factor of 3, greater than that in the south polar region. The area of the surface exposed to magnetic field lines that open into interplanetary space is much larger, a factor of 4 in the southern hemisphere than in the northern hemisphere, because these field lines are interstate highways for charged particles. I seem to have leaned on the screen here. Sorry, guys. The prediction is that the access to the surface of charged particles from the magnetosheath from the solar wind is much larger in the south. And this may play a role in the generation of the exosphere and the modification of the surface. We're testing that idea now. All right, you got a preview of this. We're moving now to some of the interesting results from the geological history. We learned a great deal from the flybys, but the ability to see the entire planet under optimum lighting conditions with targeted high-resolution imaging and to combine imaging with other data sets like topography has been extremely illuminating, has continued to inform our interpretation of what we see. From the flybys, we recognize there's a compilation of 4 examples from Laura Kerber's paper of earlier this year that there are candidates for pyroclastic deposits, volcanic centers that are marked by irregular depressions that are rimless, that are surrounded by bright material that differs in color from the ambient terrain, and that have, as best analogs, volcanic centers on the moon and other bodies that experience, at least occasionally, explosive volcanic eruptions driven by the release of magmatic volatiles during the ascent of melts from deep in the interior to erupt. This was an illuminating result for the messenger team because it said that Mercury had volatiles at depth in the past, at least in the source regions of these volcanic centers. And on the basis of the flyby data, several dozen of these centers have been documented. What we're seeing from the high-resolution observations is detailed views of some of these volcanic vents, like this one seen from the first flyby, and that's going to permit us to work out a lot of the details, to see multiple examples of eruptions, to use the ballistic equation to make statements about the required volatile content, as Kerber and all did in 2009 for this center first seen in our flyby, and to learn a great deal more about what this material is. Is it related to the sulfur that we see on this surface? That's an open question that we hope to pursue as we get more and more high-resolution geochemical remote sensing data, and the sun cooperates with flares timed to our passage over some of these volcanic centers. It was also known from the flybys that the dominant volcanic landform on Mercury are smooth plains. This is Brett Denevy's map from 2 years ago of the 40% of Mercury's surface deemed to clearly seen to be smooth plains, even though we suspected that there were many more plains that had been disrupted by impact cratering and other processes. The orbit has permitted us to take a view for the first time of the North Polar region and confirm what had been suspected for Mariner 10, but not well documented, that there is a huge expanse of plains, taken this image from a paper by Jim Head in Science 10 weeks ago, around the North Pole. This area is continuous plains material, rather uniform in color, distinct from its surroundings, and has a variety of very interesting properties. It fills these northern lowlands, although the plains now have as much as 3 kilometers of topographic relief. The edge of the plains depart substantially from an equipotential, and we think that these plains erupted in a flood lava style at high eruption rates and relatively low viscosities. And so the fact that they are not bounded by an equipotential, that they have as much relief as they do today, is suggestive of changes in topography since these plains were laid down, an hypothesis that we are pursuing now on the team. The plains have wonderful depth indicators in these ghost craters and basins. Here's one 200 kilometers across that was completely buried by these volcanic plains. All you see is a tectonic ring of ridges formed, which we think is formed over the buried rim of this 200 kilometer diameter basin, implying that the depth of fill in this area is at least something like 2 to 3 kilometers. Areas proximal to the northern plains give us a clue of the eruptive styles that must have gone on during the formation of these plains. I draw your attention to these proximal plains that are linked by a variety of channel systems, and we're going to zoom in on this area here. This is an image put together by Paul Byrne showing examples of lavas that may have come from these depressions here, but that carved channels through the older terrain by some combination of thermal and mechanical erosions, flowed and filled in a nearby impact structure, carving characteristic stream-cut islands in their wake. This is the kind of evidence that we're now amassing for volcanic styles that are signatures of high eruption rates, high temperature flows, low viscosity lavas, and flood lava-like conditions. And these are widespread on Mercury. This gives you some of the details. Comparison to topography. There's about 2.5 kilometers of relief on that diagram, showing you the downhill direction and the relationship to some of the landforms that were modified by the eruption process. The gamma ray spectrometer on Messenger is now able to resolve spatial variations in potassium. And here you see a map that Patrick Peplowski has put together of potassium in a portion of the northern hemisphere. And I draw your attention to this yellow region, which pretty much coincides with the northern plains and is telling us that the plains differ in potassium content by factors of something like 2 from the surrounding terrain. Moreover, the sun has cooperated by giving us additional high-resolution foci of X-ray spectrometer spectra, including several over the northern plains. Shoshana Weider will be giving a paper this afternoon showing that the plains differ in these elemental ratios from the non-plains regions at high northern latitudes. So what we're seeing is that the plains have a magnesium-silicon ratio that marks them as basaltic, not komatiitic. They are comparatively low in sulfur with respect to surrounding terrain. They're high in potassium. So we're beginning to be able to map geochemical variations and tie them to the geological history of the planet. We're also getting a marvelous view of the tectonics. This image from Paul Byrne shows a family of fold and thrust systems at the edge of high terrain that extends almost 2,000 kilometers. It's very characteristic of ongoing mapping of great thrust systems that tend to be at the edge of topographic highs that accommodate more shortening than we anticipated prior to the ability to make these kinds of maps. Another figure put together by Christian Klemzak zooms in on a portion of one of these fold and thrust belts here. There are a variety of ways to infer the amount of displacement and the geometry of these systems at depth, but they involve shortenings by 10 kilometers or more in many cases. In this case, as evidenced by the foreshortening of an impact crater, that's only a lower limit to how much shortening has occurred. So we're beginning to see global patterns of shortening that almost surely are the result of global contraction and are giving us totals for the contraction that are rising substantially over the numbers that were available prior to orbit. The measurements of the radioactive elements, of course, constrain the decay of heat production inside the planet and its ability to drive magmatism, to drive convection, and to contribute through the loss of heat production to the cooling and contraction of the planet. So this gives us an important context for understanding the concentration of magmatism early in the planetary history and the history of global contraction. Let me turn to these wonderful hollows that a paper by Dave Blewett first described in Science 10 weeks ago. Were not seen in high resolution during the flybys, but were seen at high resolution for the first time from orbit. Some of the characteristics of these hollows are shown here. They're almost all associated with impact craters. They're almost all associated with what had been called bright crater floor deposits. They're irregular depressions, tens of meters to kilometers across, rimless, many with bright halos, although not all, and many in families that coalesce to such a degree that the terrain looks thoroughly etched. As you see in this example here, they tend to be relatively blue compared to the average spectra of Mercury. This is an impact crater nearly 100 kilometers across, and you see some of these hollows deposits on the floor in this diagram from Blewett. Blue in this exaggerated color, and some of the details of what this terrain looks like. These hollows are seen at almost all latitudes and longitudes. They're quite pervasive over the surface of Mercury. And as we do more high-resolution imaging, we're finding more of them. So what are they? The hypothesis of the team is that they are comparatively young on the basis of lack of impact craters, and they are the result of loss of material from the surface confined to these bright crater floor deposits. Here's written as decomposition of probably volatile bearing phase by some combination of processes, heating or space weathering. And at this point, we can't prove which one it is. And that leads to the question of how these deposits were emplaced originally at Mercury's surface or subsurface, and there are a variety of ideas. They could have been material that emanated as gas, say from a volcanic eruption or an impact, and then deposited on a cold surface that was later buried, only to be exhumed later by an impact crater. They could be a product. Part of our team is looking at this idea of differentiation of impact melts as part of the cooling and modification of an impact crater. They could be emplaced at depth. In all cases, they have been exposed recently by the impact craters that bring the material to the surface, where they are unstable and gradually produce these hollows. So it's another signature of some volatile. At this point, we don't know whether it's sulfur bearing or some other species, but we hope to be lucky with the X-ray spectrometer data to zoom in on some of these terrains. Okay, polar regions. We've known for 20 years that the poles of Mercury are interesting and that they have radar-bright deposits. And the hypothesis has been that these radar-bright deposits, here you see one of John Harmon's recent radar image from Arecibo, might even be water ice. A hypothesis that is tenable because of the corollary that these deposits coincide with areas of permanent shadow on the floors of high-latitude impact craters. And because Mercury's obliquity is so small, impact craters at or near the poles indeed can have floors that are in permanent shadow. Well, we've been chasing this question with a variety of methods, and what I'm able to report on today are two methods for testing the idea that the regions seen as radar bright in the Earth-based radar images are indeed in permanent shadow. And one method we're using is altimetry in the northern hemisphere. And here you see an altimetric pass over one of these craters that host radar-bright deposits. Here you see a topographic contour map put together from multiple passes. One can illuminate this topography and learn which areas are in permanent shadow. And indeed, the areas of permanent shadow coincide with the areas, for this case, of radar-bright deposits. One can do an imaging experiment to do the same kind of analysis at the South Pole. Nancy Chabot has been leading this work. Here you see another Harman map of the South Polar region of Mercury. Again, the bright areas are areas of high radar backscatter, thought to be in the floors of impact craters. And we've had a campaign of imaging the South Pole over now more than one Mercury solar day, 6 months long. And we use these images collectively to estimate the fraction of time that each part of the surface you see there is illuminated. And that produces maps like this. And you can see the hot and the cold poles of Mercury in the non-axis symmetry. But you can also see these areas that are in permanent shadow, at least during the solar day that Mercury was observed by MESSENGER. And a simple comparison of the areas that are in permanent shadow with the radar bright deposits seen in the best resolution radar images yields this result. All of the areas that have radar bright deposits are indeed in permanent shadow in the South Polar region. So, is this water ice? The jury is still out. The instrument that's going to answer that question for us by the end of our primary mission is the neutron spectrometer that we carry. The team is hard at work. It is a difficult signal to extract, but we promise results about 3 or 4 months from now, so stay tuned. Okay, let me close with this, what I call the hyperdynamic exosphere and magnetosphere of Mercury. Mercury, the planet closest to the sun, with no permanent atmosphere, with only a small magnetic field, embedded in a very strong planetary intermagnetic field at that distance from the sun, is the most dynamic magnetosphere exosphere system. We've got a whole session this afternoon on these phenomena. And interestingly, in the context of the second lecture that many of you heard an hour ago, it is the exosphere and the magnetosphere that offer the opportunities to think about quantities that might be sought in observations of exoplanets to try to understand planet-star interactions in other planetary systems. And I'm just going to give you a flavor of the wonderful complexities of these systems. In the exosphere, we've been looking for a variety of species. We have the usual suspects, sodium, now magnesium, discovered by MESSENGER during the second flyby, and calcium. We see oxygen, confirming a report from from Mariner 10. Hydrogen is routinely observed. We've seen spectroscopically calcium +1 in the third flyby. And we're conducting campaigns for other species expected in the atmosphere on the basis of the fact that most of these species are derived from the surface, and these are all common rock-forming elements. They're not expected to be nearly as common, and you see that depicted in this plot produced by Ron Vervac and colleagues. And that's related to the probability that a given atom in the atmosphere will be detectable spectroscopically, the so-called G-value. So stay tuned in terms of these weaker species because we continue to look for them. But I want to run you through some typical Dayside and Nightside observations of Mercury's exosphere that Bill McClintock and Ron Vervac helped me put together to show you the changes with time of day and some of the dynamics of this system. So here's a typical set of Dayside profiles taken as the spacecraft flies over the day side of the planet, looking down across the front of the planet and doing profiles simply by taking advantage of the change in geometry during the trajectory. And you see plots of sodium and magnesium and calcium versus elevation, where you take elevation from where you can with the trajectory. You see that the sodium has this characteristic double trend, indicating that there are two source processes, one more energetic than the other, at contributing to the sodium, whereas calcium and magnesium can be fit by a single process. That process, however, must be more energetic than the high elevation process for sodium because it's producing detectable species at higher elevations. So it's a wonderful snapshot that we are dealing with a mix of phenomena and a mix of processes. The Nightside measurements look something like this, and they're almost all governed by the movement of the spacecraft along its trajectory as depicted in these words, which you can read, and the rotation of the spacecraft at a key point in that trajectory to give these characteristic shapes. But you can still make comparisons between species, accounting for the fact that the Nightside observations have this shape. And when you put all these data together, you can make some generalizations that seem to be holding up, but they don't apply to quite every day, but to most days. Again, sodium, the dominant species at low elevations on the day side and throughout on the night side. Magnesium, the dominant day side component here, although it wasn't in the previous slide, above 1,000 kilometers. And some other details. And so this whole system is a wonderful monitoring basis for watching the dynamics of this exosphere generation system. Here's another view. This is taken from observations near apoapsis, looking back from the night side of the planet. And you're seeing the distribution of magnesium and calcium and sodium versus local time or longitude. And you're seeing a difference that we've known since the flybys, that the magnesium distribution is most uniform, the calcium distribution is enhanced toward dawn, a very persistent result. The sodium is peaked at high latitudes. And we continue to work with ideas for what produces these very common patterns. We're also able, through the work of Sarantos and others, to actually make tomographic images of some of these species at times when we have enough crossing view paths to reconstruct the three-dimensional distribution of species like sodium and calcium. Here are a couple cross-sections behind the planet on the anti-sunward side, showing the even distribution of sodium, showing the dawn enhancement of calcium, and in fact having an abundance of calcium on the night side that's somewhat surprising relative to the expectation that many of the source processes are day-side related. So we have a lot of mysteries to solve with these data. I just want to show a couple of snapshots on the magnetosphere as my time runs down. There is an incredible richness of magnetospheric phenomena. But the University of Michigan group, Jim Slavin, Jim Raines, and others have put together a simple comparison of a quiet magnetosphere day and a non-quiet day. And Mercury goes back and forth depending on the characteristics of the solar wind interplanetary field. But here's a quiet day, and what you're seeing is the total magnetic field here. This is closest approach, or close to closest approach. Here's the Z component of the magnetic field parallel to the spin vector of the planet. These are plasma ions, protons in particular, on a log plot shown as a function of energy and time. And here you see heavy ions. And the heavy ions range from helium through heavier ions that have mass per charge ratios similar to oxygen and to sodium. And what you see is that here, near closest approach, at a point in the orbit that is normally associated with a magnetospheric cusp, there's almost no signature of that cusp. You see a nice smooth magnetic field, few, if any, enhancement of ions in this region. And you mostly see the ions in the magnetosheath where you cross the magnetopause boundary. That's a quiet day. Here's a non-quiet day. The only changes in these boundary conditions are the geometry of the solar wind interplanetary magnetic field. But look now at the total magnetic field. Closest approach is somewhere here, but it's not the maximum magnetic field. There's a huge depression of the field. Here's the B component of the field. Note the magnetopause has moved substantially closer to the planet, and you get this complex boundary. The ions are very visible in the magnetic cusp region, both protons and heavy ions. And there's a variety of other phenomena going on here and in other data sets that I don't have time to go through. But do come to our session this afternoon. There are reconnection jets. There are waves of a variety of types. There are storms of flux transfer events. This is an extremely dynamic exosphere and magnetosphere system, and one that will teach us a lot about sun-like planets and the interaction with their star. Finally, a couple of words about charged particles. Here's a nice cartoon depiction from Zurbuchen's group at Michigan of where we find the heavy ions compared to the helium ions. The heavy ions tend to be at the magnetic cusps and in the Nightside equator. In the current sheet, the helium ions tend to be more evenly distributed with position consistent with absorption of solar wind helium and then some excitation to produce the helium ions that we see. Energetic electrons we see regularly with almost every orbit. A paper by Ho et al. 10 weeks ago reported these findings from our very earliest orbits. These energetic electrons have energies upwards of 100 or 200 eV. They tend to be seen in bursts, typically at high northern latitudes, but a range of latitudes and longitudes. And even since the paper has been published, these events continue to be seen and point to some kind of acceleration mechanism within the magnetosphere of Mercury for generating these extremely high-energy electrons, first reported by Mariner 10, but now confirmed and much better documented with the messenger data. Mercury, therefore, has changed in our view, even from a time as recently as when we wrote up these papers from the flybys. You can read this better than I can from this angle, but it's a planet where the composition is different than we expected. The geology is richer than we expected. We're seeing evidence for volatiles in geological terrains as well as chemical measurements. The interaction between the exosphere, the magnetosphere, and the surface is enormously rich. And so we're still very much a mission in progress. We have more than 3 more months in our primary mission. NASA recently agreed to give us an extended mission of a second year of observations. And this wonderful diagram put together by Dan Baker shows that the extended mission puts us for the first time at Mercury in a period of the solar cycle of extraordinary activity as we approach solar maximum in 2013. So we expect to see new phenomena and an even more dynamic planet-star interaction in the time to come. So thank you for coming.
So we have some time. We have some time for questions for Sean from the fascinating talk. Please.
Any difficult questions will be answered in the sessions this afternoon.
They're all going to your posters. That's what's happening.
I did advertise the posters. Please go see the Mercury posters, all of you.
Is there there? Okay.
Yes. The question from Prentice was to note that the dimensionless moment of inertia of Mercury is similar to that of Mars, despite the very different bulk densities of the two planets. I think that's a coincidence. The compositions of the two bodies are different. As Yuri pointed out 60 years ago, we have to come up with a reason for that in the theories for how the inner planets were assembled. The moment of inertia is just the value of a particular integral, and there are lots of ways to reach that value. So I think we have a lot to learn about the interior structure of all the inner planets and how they intercompare. So your continued contribution to that topic is welcome. I hope. The question, I think that was Dave Desmarais, the lights are in my eye. The question was, in view of the fact that the core may be even larger than we expected prior to the internal modeling, how has that changed our view of how Mercury got assembled? These results are very new. We hope to be stimulating the work of the planet formation modelers in a very broad way. The cosmochemists on our team are persuaded that the starting materials, by virtue of what we see geochemically, are more reduced than those that contributed to the other inner planets, accounting for the lack of iron in the silicate, the presence of sulfur in the silicate phase, and other characteristics of what we see. That said, I think the jury's still out as to whether the high core fraction on Mercury could be the product of a late-stage giant impact that stripped off the silicate outer layer in a manner that did not substantially deplete the inventory of moderately volatile elements in that outer shell. And I am told by the modelers of giant impacts that is a possible outcome of those models. I look forward to seeing those ideas developed in the literature. So whether we needed a giant impact, I think we'll see if other models can be developed that don't. But some combination of chemical starting conditions and with or without some mechanical disruption may turn out to be the favored outcome. Right. I can't see anything in that direction, but I don't see anything. Okay, good.
All right. Well, listen, thank you, Sean, again very much for a fabulous talk. It's wonderful that we get to devote an hour to hearing the latest results from missions through these lectures. And we will give you this fabulous certificate to thank you. It's the least we can do. It's also the most we can do here at the AGU Planetary Sciences section. All right. Thank you all for coming. Enjoy the rest of the meeting.